Chapter 8, Aerodynamic Analysis for Rigid Aircraft. And the car to generate aerodynamic pressure distribution on rigid aircraft is called aerogen car. And this aerogen car is referred to by the case control car called aerogen. Aerogen always compute the rigid CP, even if you specify solution 1 in the executive control section, and then you import the structural finite element solution for flexible load analysis, but Aerogen always compute the CP on the rigid aircraft. And Aerogen also can be referred to by other cars like Flex LD, Jig Shape, Jig CP, and Trim car. And you can use plot CP to plot the CP contour. So Aerogen, you can output the CP on the ZONAIR panel model, and you can use plot CP car to look at the CP distribution. The Aerogen car refers to a Mach car. In the Mach car, you define the Mach number, and the Mach car will generate the ASC matrix. And also, if you have wind tunnel measured component loads like wind rule bending moment, wind rule shear, you can use the match LD car to adjust the ZONAIR compute CP in order to match with the wind tunnel measured component loads. You also can replace the ZONAIR compute CP by the CFD compute CP using IMP CFD or IMP CFD1 car. And also you can interpolate the wind tunnel measure CP to the ZONAIR panel to replace the ZONAIR compute CP. And so you have an Aerogen car, and you give an ID, and then this ID is referred to by the Aerogen case control command, and also Aerogen can be referred to by the Trim and Gen base and Flex LD car. And whenever you have the ID of IMP CFD, IMP CFD1, IMP DMI, or CP Spline car, if their ID match with this ID, and ZONAIR compute CP will be replaced by the CFD compute or wind tunnel measured CP. The next one, the ID Mach, refers to a Mach car. In the Mach car, you define the Mach number, and alpha, beta are the angle tach and side slip angle. P rate is the non-dimensional roll rate. Q rate is the non-dimensional pitch rate. R rate is the non-dimensional yaw rate. And after that, the label refers to the label of AE sub Z or AES link control surface, and then you give a deflection angle in degrees. So this defines the flight condition of for generate the CP under this flight condition. Also, you have a step DRV. If step DRV equals yes, and the Aerogen car will also compute the aerodynamic stability derivatives. And also, you will generate another set of AIC for computing the flexible loads. And so the step DRV, once you turn on, you will increase the computational time of the Aerogen car. The Mach car is referred to by the Aerogen car, and you define a Mach number, and if you say method equal to 2, and then you use hypersonic aerodynamic method, and the viscous refers to a viscous car, and to define the viscous parameters for skin friction computation, and also to introduce the viscous vortex model for the C-rock element, because as we mentioned, C-rock element is a line vortex. At the center of the line vortex, the velocity is infinity, and then you can in a viscous car you can use different models to introduce the velocity inside the vortex core. And here you say save or acquire. So if you save, you will save AIC. If you say acquire, you will acquire the AIC matrix. And the file name is a file to save this AIC matrix. Okay. In all ZONAIR input cards, whenever you want to specify a file name, and we only give you 16 columns to specify this file name. If the file name is too long, and you always can specify a $sign and followed by an integer. This integer refers to the exe file. So in this card, you can specify a much longer file name. Because the AIC only depends on the Mach number, it's independent of the flight conditions. So once you save you have the AIC, you can acquire the AIC. Then you can use different aerogen car and with a different flight condition, and so ZONAIR can rapidly generate the aerodynamic solution at different flight conditions. And low Mach car defines a component load. This low Mach car is referred to by many other cars. And the first, you want to specify a set of aerodynamic panel ID by referring to panels 1, panels 2, panels 3. So ZONAIR will integrate the aerodynamic pressure on those panels to give you aerodynamic component loads. And so you then you define a coordinate, and then you specify what type of component loads. You want shear force along XYZ or bending moment about XYZ of this core to our car coordinate. And set G refers to a set 1 car. In the set 1 car, you specify the ID of the structure grid, which within this component loads region, and then it is used only for flexible loads analysis. Match LD. In case you have a wind tunnel measured component loads, and you want to use this component loads to further adjust ZONAIR compute CP. So after you adjust the CP, when you integrate the CP, will agree with the wind tunnel measured component loads. So this ID arrow refers to the ID of aerogen car, and this is the dynamic pressure and in the wind tunnel when you measure the component loads. And then you give a low Mach car ID, and then you give a value, which is this value is measured by wind tunnel testing. And so you can specify many component loads like wind rule bending, wind rule shear, wind rule torque, and so on. And so the match LD, we use a Lagrange multiplier method to adjust the ZONAIR compute CP in order to match with the wind tunnel measured component loads. And the ZONAIR compute CP and generated by the aerogen car is called CPZ, and the salt corrected pressure coefficient is called CPZ. And so the difference between these two sets of CP, we want to minimize that. In other words, the match LD using the Lagrange multiplier method to using minimum amount of delta CP and put on the aerogen generated CP. And after you have this correct CP, and then you multiply the CP by SKJ matrix, SKJ matrix is to convert this, the CP to forces. Then you multiply by a Lowe's integration matrix. This Lowe's integration matrix is defined by Low markup, and multiplied by the dynamic pressure. This will give you the component loads, and this component loads must match with the given component loads. So this becomes a constraint function, and so this is the Lagrange multiplier method to calculate the CPC. In case in the wind tunnel testing, because the wind tunnel model may have a gravity force. So you have Nz equal to 1g, and so you want to include the inertial effect, and if you say Nz equal to 1g or 386 inches per second squared, and you multiply by a rigid body plunging mode, and then multiply by the GZ mass matrix, this will give you inertial forces at the structural grid point, and then the structural grid point multiplied by a Lowe's integration matrix. This will give you component initial component loads, and the difference between the aerodynamic and inertial loads will is forced to match with the given component loads. So after that, you have this adjust CP, and plot CP. You can plot the CP on the aerodynamic model, and so this ID match with the ID of the aerogen car, and type equal to yes or no. If it's yes, then the control surface deflection angle is included in the plot file, and depends on what kind of a graphic software you have those choices, and then you can generate a file which can be read in by those graphic software. This is another option for form. If form equal to output 4, and the plus CP card will save the CP in output 4 format to this file, and in this plus CP card, you will include the pressure coefficients and the local Mach numbers. And if you have IMP CFV, IMP CFV1, CCP spline, CCP spline 1 car, CP spline L car, if the pressure distribution on the panel model computed by Aerogen car is replaced by the CFV wind tunnel result, and then you can save those, interpolate, replace the CP into the output 4 format. And this is one example we call L51 F07, and we have this is a so-called thick wing model, and then we use slice car to slice the wing trailing edge, and slice the wing tip, and we put C-rod elements along here, C-bar elements along the trailing edge. Then we generate RBE2, and then we use auto bar to place the CC bar elements around the end of the body. And we also model the wing using the thin wing approach. So the car is called C07, and then we have a 16 spanwise card, 15 coils card, and the spanwise card is defined by the AFAC card with ID 201, and the airfoil section is defined by PA47 card with the ID 205, and then at the root of the 07, we say yes, so it's attached to the body, and then 202 will become a set 1 card. This set 1 card lists out the structural grid point along the the body where the wing root of the CO7 are attached to. And 203 it lists out the 7 car, which lists out the RBE2 grid after the wing trainage on the body. So you can use plus CP car to look at the CP distribution, and then we compare the thick wing modeling result and the thin wing modeling result with the wind tunnel. So the wind tunnel data on the upper surface of the wing is open circle. The lower surface is open triangle. The thick wing on the upper surface is represented by the solid line. The lower surface is by dashed line. The thin wing model is a line with a circle and a dashed line with a circle. So overall, speaking, at the low Mach number, the ZONAIR solution, both the thick wing and thin wing solution, compare well with the wind tunnel measured data. But if you look at the thin wing modeling, the thin wing model result overshoots the leading edge CP, and the thick wing compute CP agree well with the wind tunnel data. At Mach 0.9, then you can see that actually you have a transonic shock here, and this shock cannot be captured by ZONAIR, and this is supersonic Mach number 1.2. And then this is a higher angle attack at 4 degrees. Again, at Mach 0.9, you can see there's some disagreement between ZONAIR result and the wind tunnel measured one, because at Mach 0.9 angle attack 4 degrees, transonic shock occurs at the upper surface of the wing. And this is the CP along the fuselage. And we can compare the normal force at different Mach number with the wind tunnel data. So both thick wing and thin wing compare well with the wind tunnel data. And this is the CM, and this is the induced drag comparison. Okay, the next one we want to talk about how to replace the ZONAIR compute CP by CFD compute CP. If the CFD code is a structured match, and we use the IMP CFD. So the ID CFD, if it match with the ID of Aerogen car, then the Aerogen compute CP will be replaced by the CFD compute CP. Also, if ID CFD is a negative integer, it is referred to by trim IMP car, and to compute the pressure derivatives with respect to the trim variable, and we're going to talk about this in the trim module. And because you want to replace ZONAIR compute CP by CFD compute CP, in this case, you may not need to generate the AIC matrix. So you can use the parent Vortex account with entry name equal bypass to bypass the AIC generation. And this is this one refers to a quad account if the CFD mesh is located in a different coordinate from the ZONAIR aerodynamic coordinate system, and then you can use quad account to transform the CFD mesh to the ZONAIR coordinates. And the omit CFD and you can omit some CFD mesh from the CP interpolation, and form CFD, because the structured CFD solution has a standard format called plot 3D, but the plot 3D may be in ASCII file or a binary file, or even you may have an iBlank array or not. So you have different type of format. So this one tells ZONAIR what kind of format of this structured CFD solution, and CFD mesh contains is a file name that contains the CFD mesh, okay, and the CFD out is a file name contains the CFD solution. Okay, so from the mesh, from the CFD, and ZONAIR can interpolate the CFD computer CP onto the ZONAIR panel model. IMP CFD1 is for the unstructured CFD, again, this one is referred to the idea of Aerodynamic car, and if it is negative, and it is referred to by the trim IMP car, and again, you can transform the CFD mesh to the ZONAIR aerodynamic coordinate. The data, you have several options because the unstructured CFD solution does not have a standard format. Okay, so you have plot 3D, you have a fun 3D. If it's fun 3D, then the CFD solution are computed by the fun 3D code. If data equals CFX, then the CFD solution are computed by the CFX2 code. And CFD file is a file name that contains the unstructured CFD mesh and the solution. Okay, and then because the CFD solution are non-dimensional, so you have to tell ZONAIR how do you normalize this flow quantity by different method. Okay. Also, X scale, if the CFD mesh, the length unit is different from the ZONAIR length unit, so you have to use X scale to make the same length unit between those two models. Gamma is a specific heat ratio, and then this file mesh is a file name to store the ZONAIR panel model and the CFD surface mesh in what kind of format, and then you can plot this the ZONAIR panel model and the CFD surface mesh. Make sure they overlap on top of each other, and the file SOL is another file name to store the interpolated CP and the Mach number, and the PINF if the data equals CFX, because CFX solution is dimensional, so you have to specify what's the dimensional free stream pressure. Okay, then ZONAIR can convert this dimensional flow solution into non-dimensional. IMP DMI is that after you replace the ZONAIR compute CP by CFD, or when to measure the data, then you can use the plot CP cars, and you specify form equal to output 4, and this CP will be saved into this file into the output 4 format. And the next time, if we want at the same flight condition, and then you can retrieve this CP using IMP DMI car. Okay, and again, the ID arrow match with the ID of Aerogen, and also ID arrow can be a negative integer, and then it is referred to by the trim IMP car. and we're going to talk about this card in the trim module. And CP spline is to interpolate the wind tunnel measured CP onto the ZONAIR model to replace the ZONAIR compute rigid CP. So the ID arrow is the ID of aerogen. Again, it can be an active integer, so it is referred to by the trim IMP card. And the scale is that the wind tunnel model size may be different from the full scale model. So you want to use the scale factor. And ID core is that the wind tunnel model may be in a different coordinate, so you want to define a contour card to transform the wind tunnel model from to the ZONAIR aerodynamic model. A file WT is a file name to specify an ASCII file where the wind tunnel measured pressure coefficients are stored. Okay, then this plot file to store the wind tunnel measured the sensor CP sensor locations and the ZONAIR panel model include both in this file. Using this format, then you can plot it to make sure that the overlapping between ZONAIR model and the wind tunnel CP sensors. And to do the spline, CP spline is based on so-called component by component basis. And so you do this open-ended Volta card. So on each line, you specify a method. The method can be IPS for infinite plate spline, TPS for thin plate spline, which is a 3D spline. A beam spline is a beam spline. Okay. Then this one is CP is the ID of a contour card, and if you use infinite plate spline, and you need to specify a spline plane. So this spline plane is defined by the XY plane of this contour card. If you use a beam spline, and the beam spline needs a spline axis, the y-axis of the contour card is the spline axis. If you use TPS, it's a 3D spline, then you don't need to define a contour card. And set K, you want to define a set of ZONAIR panels, which would be spline the wind tunnel CP to those ZONAIR panels. And set G, it refers to set 1 card. In set 1 card, you list out the wind tunnel pressure points. So you want to interpolate the pressure at those points to the ZONAIR panels. And DZ is a linear attachment flexibility for least square approximation. And EPS defines a very small tolerance. So the tolerance is computed by EPS times the REFC. REFC is the reference core defined in the AeroZ card. And because the spline method does not allow two pressure points located too close, if they are located within this tolerance, it is a fatal error. PROJ is projection. If yes, and all the aerodynamic panel here and the wind tunnel pressure point are projected to XY plane defined by this contour card. And then this projection file can be saved here. Okay. And CP spline L is also to interpolate the wind tunnel measure CP onto ZONAIR panel model, but by a linear spline method. And the difference between CP spline and CP spline L, the CP spline will use the infinite plate spline or thin plate spline to spline the CP not only along the clockwise direction, also along the spanwise direction. But CP spline L, they use a linear spline for interpret the CP along the spanwise direction. Okay, so because the wind tunnel pressure sensor locations are usually much closer than the ZONAIR model, mapping the wind tunnel measured pressure onto ZONAIR require interpolation and extrapolation. In the CP spline car, the IPS, TPS, and beam spline can be selected for pressure mapping. The selection of the best method for pressure mapping requires a trial and error procedure. The wind tunnel measured pressure distribution may have large variation, especially around the wing leading edge. So span method without least square approximation may have overshoot in the interpolated pressure distribution, especially around the wing leading edge. So the entry DZ in the TPS and IPS can relax the deformed plate, and by a least square method, the best value of DZ also requires a trial and error procedure. So this is the one example, and this a ZONAIR model, and the green circles are the wind tunnel CP sensor locations. And so we want to interpolate this onto the wind tunnel measure CP onto ZONAIR panel model. So we do a component by component basis. First, we want to use a 3D spline to spline the pressure on the fuselage, then also the engine nacelle using 3D spline TPS, and for the wing leading edge, we use the thin plate spline method, and for the rest of the point on the wing, we use the IPS method. For the horizontal tail, we also use the IPS method. So the wind tunnel model scale is 1/25, and the y-axis is along the span, and x-axis is along the fuselage. So TPS, the 3D spline method, is applied on the wing leading edge. The pressure sensor location in the wing leading edge are in 3D space, so we can use the 3D spline. And we found out we have to use very large DZ for least square. IPS method is applied on the wing, excluding the leading edge, and the two IPS are applied on the upper and lower wing surface separately, and as well as on the horizontal tail, and DZ equal to 0.1 is used for least square. So this is the car. This is an Aerodynamic car, and with this ID, and it will refer to a Mach car, and the Mach number is at 0.6. We acquired the AIC, and the angle tach is at 5 degrees, and the aileron is at 25 degrees deflection, and this is for the fuselage, and this is for the engine nacelle, and this is for the pylons. They all use the 3D TPS method, and we scale up the wind tunnel pressure model by 25 times, and this is referred to a control car, and which transform the wind tunnel CP sensor locations to the ZONAIR aerodynamic coordinates, and this is the file name which contains the wind tunnel measured CP. So each CP sensor has an ID, has XYZ location, and the measured CP. And then you can generate a file. You can verify the overlapping between the wind tunnel CP sensor locations and the ZONAIR panel model. So we use TPS for fuselage and for the engine nacelle and for the pylons. And this is for the wing leading edge. We use TPS with a very large DZ, and this is IPS, infant plate spline method for the CP on the upper surface of the wing, and excluding the leading edge points. And because IPS, we need to define a spline plane, and this is referred to a contour car, and XY plane of the contour car will become a spline plane for IPS. And so this at Mach 0.6, aileron is at 25 degrees, angle attack is 5 degrees. So we have on different span station, and we have 3 setup for CP. The open black circle are ZONAIR compute CP. The red open circle are interpolate CP. The blue diamonds are the wind tunnel measured CP. So you can see, because at this Mach number, this low angle attack, ZONAIR's potential theory is valid. So in general, the ZONAIR compute CP compared to the wind tunnel measures CP, the agreement is quite good. Okay, and but however, near the wing leading edge, and the wind tunnel measured CP has a spike here, and this spike is not captured by the ZONAIR solution. However, if you look at the interpolate CP, and it can capture such a spike. The large difference between the ZONAIR solution and the wind tunnel model is on the aileron. So if you look at, because the aileron is at 25 degrees deflection angle, so if you look at the wind tunnel measure CP on the upper side of the aileron, it's almost a flat line. That indicates the flow on the upper surface of the aileron are already separated. But ZONAIR is attached flow theory, so the flow remain attached. So this is a hinge line location of the aileron, and so we have a large difference. And but if you look at the interpolate CP on the ZONAIR panel model, which agrees well with the wind tunnel measure CP. This is at Mach 0.6, angle attack 5 degrees. And also we can plot the CP contour using the plot CP car, and also at different angle attack, we can use the CP spline to spline the CP onto the ZONAIR panel model at different angle attack, and ZONAIR will integrate the CP to give us the CL, and then the red line is the CL computed from the interpolate ZONAIR CP. The black line is the CL computed by ZONAIR itself. The next Mach number is at Mach 0.785. Then the angle attack 5 degrees, and then you can see the wind tunnel measure CP clearly show that there is a transonic shock occur, and such a transonic shock cannot be captured by the ZONAIR. Okay, so there's a large difference between ZONAIR solution and wind tunnel measure data. However, if you look at the interpolated CP on the ZONAIR panel model, it agrees well with the wind tunnel measure CP, and also you can integrate the CP to give you the CL, and showing by the red line, and the black line is the ZONAIR compute CL. The next case is for a business jet, and we have a CFD model, and we want to replace the ZONAIR compute CP by the CFD generate the CP. So it is unstructured mesh. So we use the IMP CFD1 card. So first we can we can output a graphic file and which contains both the ZONAIR surface panel model and the CFD surface mesh, and we can plot them together to verify the overlapping between those two meshes. And then we use IMP CFD1 card, and this is the CFD solution at Mach 0.84, angle attack equal to 2 degrees, and this is the interpolate CP on the ZONAIR panel model. So you can see they have a very good agreement. And next one, we also have the wind tunnel measured CP. So the measured CP on the wing is available at those span station. So we use a spline L for the wing, and the CP spline for the winglet. And so we have three set of solution. The first one is ZONAIR compute CP contour. The next one is wind tunnel mapped CP onto the ZONAIR panel model. The third one is CFD mapped CP onto the ZONAIR panel model. And there's a difference because if I remember correctly, the Mach number for the wind tunnel measured CP is at angle attack 1.7 degrees, and whereas the CFD compute CP is at angle attack 2 degrees. So this is the wind tunnel data. This is the mapped wind tunnel CP on ZONAIR panel model. You can see they have a good agreement along this span station, and this is the mapped CFD CP. The difference between CFD and the wind tunnel is this angle attack is at 1.7 degrees. This is at 2 degrees. But if you look at the ZONAIR compute CP using the potential theory, it cannot capture this transonic shock. So this at another span station, another span station, this at another span station, and another span station. So finally, let's summarize how we're gonna replace the ZONAIR compute CP by the wind tunnel or CFD data on rigid aircraft. So first, you specify aerogen card, and then you can use either the CFD computed CCP or wind tunnel measured CP to replace the aerogen generated CP. And after that, and if you have a component loads measured by the wind tunnel testing, such as wind rule bending moment, and shear and torque, then you can use mesh LD to further adjust those CP in order to match this component loads. So the mesh LD will further adjust the CP, even is computed by CFD or measured by the wind tunnel, because the wind tunnel measured CP is at the CP sensor locations. They are very close. So this interpolation may introduce error. So you want to further adjust those CP in order to match wind tunnel measured component loads. And after that, you can store this CP using the plus CP card with form equal to output 4 into a file. Then later on, if you want to do flexible loads, and of course you want to import the structural finite element solution using a sign matrix equals executive control command, and then you import the adjust CP by the IMP DMI card, and with the file name generated by the plot CP cards, and then you have adjusted CP on the rigid aircraft. Then you can perform static area elastic analysis to flexibilize the rigid CP. Okay, this is the end of section 8.